Hey guys, I hope you're having a good night. We're going to be looking at graphing quadratic equations using the form of y equals ax. This is the most simplest form we can graph in, the very basic form. So let's get started with that title. Again, graphing y equals ax. Your essential question is, what are the characteristics of y equals ax? We could also change that word characteristics to what is the landmarks of y equals ax. What does a, this very beginning coefficient, remember, what does a do to the graph? Very basic, two of the basic characteristics of quadratics is what we call the vertex, and the vertex is at which the parabola, the U-shape, goes from increasing to decreasing, or in this case, from decreasing to increasing, that point at which it changes direction. Okay. The second way we describe them is with the axis of symmetry. You see this little dashed line right here? This is your axis of symmetry. This is where we could fold the paper up and then match up because there's symmetry there, okay? This is where you're talking about like a reflection across this y-axis, axis of symmetry. Next, we characterize them with, there we go. We characterize them with increasing or decreasing values, and that usually goes with the domain and range, okay? So, right here, this blue graph right here is a normal where a is 1, where this a is 1. A normal, but the very most basic one. This is the normal graph. Okay, now, the green one, when a is bigger than 1, we get this skinnier graph. So what does a do to it? If it's bigger than 1, it becomes skinny, and this is the green one. When a is between 0 and 1, okay, what happens to it is it gets wide. So wide, skinny. Now, we also need to look at what happens when a is negative. So let's go look at what happens when a is negative. It just flips it. It reflects it by flipping it. Still symmetry, still has that vertex, okay? Here's your normal when a is negative, normal. Now, when a is in between -1 and 0, it still gets wide. And the green one, it still gets wide. The green one still makes it skinny. All that negative sign does is flip it upside down, okay? Now let's go ahead and practice identifying characteristics. There's 6 basic characteristics when it comes to any function that we're talking about. The first one is vertex. The second one is an axis of symmetry. Okay, the third one is the y-intercept. The fourth one is the x-intercept. Or at more than one, because look right here, we're looking at more than one. The fifth one is domain, which we haven't talked about in a while. And the sixth one is range, which we also haven't talked about. When you're asked to identify or describe a graph, here's what you're using to describe it. First of all, the vertex is the point at which it changes from increasing to decreasing. We say 2, 8. The vertex is 2, 8. Axis of symmetry. This reflection right here, where we could fold it up and they line up, is at axis of symmetry is that x equals 2. This line right here where x is 2. Third one, y-intercept is right here at 0, 4. Your x-intercepts, we're going to have to approximate them because they're not right on the line. So we're going to say about -0.9, 0 and positive 4.9, 0. -0.9, 0, positive 4.9, 0. Domain. Remember, domain goes with the x-axis, and so when we squish this whole thing, we're going to sandwich this. When we squish it, what happens to our function is that all the numbers on the x-axis do have an output. So all real numbers, the range, remember, has to deal with the y. And if we squish it, let me go ahead and erase some of this so we can see what the range will look like. When we squish this function, as if we're going to like take our picture and like squish it down, we'll hit not all the y values. Okay, we're squishing it on this y-axis. It will be, see, nothing past 8 on the y-axis is going to be hit. So it will go from the range of -infinity to 8. That's your range. That's all we need to do in order to be able to describe all of the landmarks of a quadratic function. So now let's go ahead and look at graphing two equations. When we compare, we're going to look at what's the same and what's different. That's what compare means. What's same, what's different. So when we graph them, we start off with tables, just like what we practiced today, x, y, x, y. There's symmetry on these ones because they have no plus anything around the origin. So let's start off at 0. Let's go to -1 and -2. Positive 1, positive 1, positive 2. -2, -1, 1, 2. All right. -2 squared, -2 squared, again, is -2 times -2, which is 4. Divided by 2 now is 2. Let's go here to 1. -1 times -1 is 1, and then 1 times 1/2 is 1/2. 0 times 0 is 0. 0 times 1/2 is 0. And here's the symmetry part right here. 1 times 1 is 1. 1 times 1/2 is 1/2. And then it's going to mirror. This one's going to be 2. Let's graph this one. -2 squared is 4. -1 squared is 1. 0 squared is 0, and here's our symmetry, 1, 4. A for our first one is less than 1. A for our second one is equal to 1. So let's go back to our beginning of our notes and look what happens when that is the case. The beginning of our notes, we find out right here, when A is equal to 1, we have this normal average parabola. When A is greater than 1, it gets gets skinnier. When A is less than 1, it gets wider. So we already know when we're comparing them, we already know that we are looking here at something that is going to be wider. In our graph, and you should have a perfect graph, not a sketch. This is a sketch for me because you have graph paper, okay? Our first one, -2, +2, -1, +0.5, 0, 0, and it's going to mirror that. Here's our first parabola. Our second parabola, -2, +4, -1, +1, 0, 0, and it's going to mirror that. Compare, how are they similar, how are they different? They're both a parabola, they both have a vertex at 0, 0. They're different because y equals 1/2 x squared is wider than y equals x squared. We call A, by the way, stretch factor. So the stretch factor makes it wider. A makes it wider. Let's go ahead and look at our next example. Let's make our tables. So let's make our table for our first one. The symmetry is going to be about 0 because it doesn't say plus anything, okay? So we're going to go to -1 and -2. We're going to go to +1 and +2. -1 squared is +1 times -1/8 is -1/8. -2 squared is +4, and +4 times -1/8 is negative. So +4 times -1/8 is -4/8, which reduces down to 1/2, -1/2, and then 0. Luckily, it mirrors this because it has no plus here, didn't shift it. So this is going to be -1/2, and this is going to be -1/8. So our first one's done. Let's make our second one, second table. -2, -1, 0, 1, 2. So -2 times -2 is +4. -1 times -1 is 1. 0, 1, 4. Our graph. We're going to compare the graph. What do they have in common? What do they don't have in common? We know for this first one that A is -1/8. A is less than -1, which does something specific that we looked in our notes about. So let's see what happens. We have -2, -1/2, 1, -1/8, 0. Now it's going to mirror that. Okay. Yours should look much better because you have graph paper. Let's graph our second one, our parent. This is called a parent. -2. Oh, these are all negatives. There we go. Oh, wait, no, they're not negatives. Go back, they're positives. -2, +4, -1, +1, 0, 0. It's going to mirror it. All right. How are they same? How are they the same? Okay. They're both parabolas. They have the same vertex. They have the same axis of symmetry. They have the same domain. They don't have the same range. The -1/8 one is wider and upside down. Make sure you're using those 6 ways of describing graphs to compare them, okay, that we talked about. Go ahead and try these on your own problems when you're ready to